Welcome to this particular module, and this is the module for our lecture where we are looking at filters, right. So, we have seen band, we have seen the filters that will pass a particular band and it will filter out particular band, correct. So, we have seen low pass filter, we have seen high pass filter. Low pass filter we have seen passive filters and we have seen active filters. Same way in high pass filter we have seen passive filters and we have seen active filters. Now, let us focus on low pass and high pass combination. So, what will happen? It will be a band pass, it will be a band pass filter. So, how exactly band pass filter we can design using operation amplifier? Let us see it. Okay. So, we will see two kind of filters, one is band pass filter and another one is band reject filters, and we will take some examples. So, you can understand how we can design these circuits, alright. So, if you come back to the screen, and what you see here is a band pass filter, correct, band pass filter. Now, the principal characteristic of a band pass filter or any filter for that matter, it is its ability to pass frequencies relatively unattenuated over a specific band, or spread of frequency called pass band and attenuate the other band of frequency called stop band, correct. We have seen this, that when you design a filter, a certain band of frequency is allowed to pass, which are called pass band frequencies, and certain frequencies that we do not want, they are attenuated, it is called the stop band frequency, it is called the stop band frequency. Very simple, right, it is very simple. Now, a simple band pass filter can be easily made by cascading a single low pass filter with a single high pass filter. Super easy, right. If we know how low pass filter circuit is, if we know how high pass filter circuit is, then by cascading low pass filter with a high pass filter, we can design a band pass filter, we can design a band pass filter. So, if there is a block diagram, it is a high pass filter at the starting of the block, this is block diagram for the band pass filter, alright, this is a band pass filter. The first block is high pass filter, then we have to amplify, then low pass filter, alright. So, high pass and low pass combination of this, cascading of this will result in a band pass filter. Input peak to peak with certain frequency, we will see what is the output, which frequency it can pass, alright. So, the cutoff or corner frequency of the low pass filter is higher than the cutoff high pass filter, and the difference between the frequencies at minus 3 dB point will determine the bandwidth of the band pass filter, alright. So, what does it mean? The cutoff or corner frequency of low pass filter, right, is higher than the cutoff frequency of high pass filter, right, and the difference between this frequency, that means if I draw, right, the cutoff frequency of the low pass filter and the cutoff frequency of high pass filter, right, the difference between it, that means this is the difference, that is the band which will be allowed to pass. So, this is the pass band, this is the pass band, and this is the stop band, right, stop band, this is also stop band, right. This is what it means by this sentence, okay. The cutoff frequency or corner frequency of low pass filter is higher than the cutoff frequency of high pass filter, right. So, if this is my cutoff frequency for low pass filter, this is higher than the cutoff frequency for my high pass filter, right, and the difference between two, that is this difference is my band of frequencies that I want to pass, and it is my band pass filter, it is my band pass filter. A simple band pass filter, alright, a simple band pass filter, how we can design? We can use high pass filter stage, we can use low pass filter stage, we can cascade both the stages, right. So, you see here we have capacitor and resistor, this is our high pass stage. I apply a signal, right, to the capacitor, and you know how the high pass filter works. This output of the high pass filter is fed to the low pass filter, and thus what will happen in this particular case, in high pass filter you can have a band of frequencies that will pass above this FL, above this FL, right. In case of low pass filter, there will be band of frequencies that will pass below this FH, below this FH, that means this one, right, this particular band, correct. So, if I merge both, if I cascade both, what will I have? I have my band pass filter. So, this cascading together of individual low pass and high pass filters produces a low Q factor type filter circuit, which has a wide pass band, which is a wide pass band. Very easy to understand band pass filter once you know how the low pass and high pass filter works. So, we will do this experiment also, it is called Simulink. Okay. We will perform a simulation with a software, right, and we will see how we can design the circuit using a Simulink and how we can obtain this point, obtain this plot for the band pass filter. This will perform in the experimental portion. When we perform the experiments for designing the filters, we will see how we can design a band pass filter. In general, we will see how we can get the source from the library, how we can select the capacitor, how we can define different values of capacitor, how we can define and drag the resistors, how we can connect these resistors, how we can connect these capacitors, how we can select the ground from the library, and how at what point we want to see the output voltage when we design this thing and we apply a 15 volts peak to peak and with a certain frequency, right, that we have selected, and we have to understand that what is the band of frequency that is allowed to pass. We will be able to see that whatever frequency we have selected, the minus 3 dB that we have to calculate, minus 3 dB. So, it will be band like this that is allowed to pass and rest of the band is not passed, thus there is a band pass filter, it is a band pass filter. So, let us take an example to make it easier. Let us take an example to make it easier. Design and band pass filter with a low cutoff frequency of 2 kilohertz and with a resistor value of 10 kilo ohm, high cutoff frequency of 10 kilos, capacitor value of 5 picofarad. So, what is given? FL is given, right, FH is given, see FL is given, correct, FL is given, FH is given, this is your FL, this is your FH, right. Now, you are given R, where is the resistor? Here. You are given C, which is here, right. So, we know that F equals to, correct. So, from here we can find C equals to 7.9 picofarad, correct. Now, we for second one we know that this is for first one, right. So, F again F equals to, so FC1 FC2 we can say like this 1 by 2 pi, right. So, this one we have calculated because we know value of R1, but we do not value of C1 we do not know. Here we know value of C2, but we do not know value of R2, right. So, first is the equation for FL, this is equation for FH, right. From here and from here we can find, so R1 C1, R2 C2. So, here what is given? We are given value of FL, then we have R1, what we do not have? C1. So, C1 would be equal to 1 upon 2 pi FL into R, we can substitute value 1 upon 2 pi FL. What is FL? FL is 2 kilohertz into resistance, resistance is 10 kilo ohm, correct. So, we will get value of C1 equals to 7.9 nanofarad, we get C1 equals to 7.9 nanofarad, beautiful, very easy. Now, let us see how we can find value of FH, and using FH how can find R2, how you can find R2. So, FH, what we have written, FH equals to 1 by 2 pi R2 C2. What we have? We have FH. What we have? We have C2. What we do not have? R2. So, R2 will be 1 divided by 2 pi fH C2, right. So, this will be 1 divided by 2 pi fH. What is fH? 10 kilohertz, right, hertz, into C2 500 picofarad, 500 10 to the power minus 12. So, that will give us 3.18 kilo ohm, that you can see here, 3.18 kilo ohm, correct. So, using the given values you can design a band pass filter, very easy, right, absolutely easy. You have to just understand and remember one equation, and then you can easily design the circuit, that is your band pass filter. Now, if you are given a circuit, right, again this is a band pass filter, and you are applying the signal to the inverting terminal. So, it is a inverting amplifier, right, inverting amplifier we understood. So, gain of inverting amplifier we already know, minus R2 by R1, right. Frequency we know f equals to, let us say we write FC1 and FC2, right, because we have band pass. So, FC1 FC2, correct. So, we will write FC1 equal to 1 by 2 pi R1 C1, FC2 1 by 2 pi R2 C2, correct. And gain we know this formula, right. What is gain? Calculate the higher and lower cutoff frequency of active band pass filter as shown in figure, find out its gain. First, let us find out its gain first, right, gain first. So, R2 by R1, 10 by 10 minus R2 by R1 minus 10 by 10, gain equals to 1, easy, super easy, right. Now, let us see the cutoff frequencies. So, FC1 equals to 1 upon 2 pi R1 into C2, right, because C2 is here, R1 is here, right. FC2 1 upon 2 pi R2 C3, right. Substitute the values, substituting values, what we get? We get the value of FC1 and FC2, easy, very easy, right, super easy. Then let us do one more problem, let us solve one more problem. Design a band pass filter so that FO equals to 2 kilohertz. You see different way of putting the things, some people say FC, some say FL, FH, some say FO, right, does not matter, do not worry about it, never get confused with this kind of terms, right. So, we know FO 2 kilohertz, quality factor 20, C equals to 1 microfarad. In this case central frequency FO. So, what is FO? See central frequency. So, you have this, right, FL, FH, right, and this will be center frequency, okay. So, FO, right, and quality factor can be FO divided by bandwidth, quality factor can be FO divided by bandwidth. So, when I say people say FH, people say FL, people say FC, people say FO, this is terms for everything, okay. That does not mean that everything is same. This is critical frequency, this is central frequency, this is higher cutoff, this is lower cutoff. So, you have to understand what are the terms, but the point is do not get confused if you see a suddenly new term, do not get confused, okay. The central frequency is given by FO, you have seen here, right, for this particular plot. This is again your gain in decibels, this is your frequency in hertz, correct, and then Q equals to FO by bandwidth. What is bandwidth? Bandwidth is nothing but lower frequency minus upper frequency, right, FL minus FH, or higher frequency minus lower frequency. So, it terms is positive, right, if you have this FH, FL, right, FO, bandwidth FH minus FL, right. So, we have written Q equals to FO divided by bandwidth, FO divided by FH minus FL, substitute value Q equals to 20, right, then FO is 2 kilohertz, right, divided by FH minus FL. So, FH minus FL will be 0.1 K. Now, FO equals to under root of FH into FL, that also we know, right, which is nothing but FH FL equals to 2 K whole square equals to 4 m, right. Now, FH minus FL whole square is what is like similar, right, this is very easy, you see mathematics. So, easy math, basic mathematics. What is this? A minus B whole square equals to A square plus B square minus 2 AB, right. This is what is written, FH square plus FL square minus 2 FH into FL. This is nothing but FH square plus FL square minus 2 times 4 m. So, when we substitute the value we will get this. Finally, when you solve this equation, when you solve this equation, you will get FH plus FL is 4.001 K. On solving, FH equals to this one and FL equals to this one. So, FH equals to 1 by 2 pi RC, R1 equals to this, FL equals to 1 by 2 pi RC, R2 will be this value, R2 will be this value, correct. So, this is how we can design the band pass filter, this is how we can design the band pass filter. Now, once we have seen how the band pass filters can be, designed, let us see how band stop filter can be designed and what are band stop filters, what are band reject filters, right. So, you see here the plot, if you see the plot, what you see is this is the band which is stop band, this is the pass band, this is the pass band, right. So, this is ideal, in actual you will get something like this. All right. This is the plot for response plot for band stop filter, that means a particular frequency that we do not require, a particular band of frequency that we do not require, we can stop it by designing a filter using a operational amplifier, right. The figure shows ideal frequency response of band stop filter. The band stop filter is formed by combination of low pass and high pass filters, okay. So, band stop filters can be again designed or can be formed by using low pass and high pass filter. In case of the band pass filter, it was high pass and low pass. In case of band stop, low pass and high pass with a parallel connection instead of cascading connection, you see. So, in case of band pass filter, we were cascading low pass filter and high pass filter. In case of band stop filter, we are connecting low pass filter and high pass filter, but in the parallel connection, in a parallel connection, okay. So, you remember that when you have to design a band reject filter or band stop filter, you have to connect your low pass and high pass in a parallel connection. The name itself indicates it will stop a particular band of frequency. Since it eliminates frequency, it is also called band elimination filter or band reject filter or notch filter, you see. So, it has lot of names, right, lot of names. What are the names? Let us write down: band stop filter, band reject filter, band reject filter, band elimination, band elimination filter, also called notch filter. Notch filter, you see 4 different names for band reject filter: band stop, band reject, band elimination, notch filter, alright. So, any question comes to your exam or any question comes in your interview, then you can answer that yes, we know all these filters because all these filters are the same filter, which is my band reject filter, okay. So, it is called by many names, it is called by many names. Very easy, right, very easy to understand op amps and its application, isn't it. So, the band stop filter is formed by combination of low pass and high pass in a parallel connection, right. Second is it will stop band of frequencies, it is also called band reject, notch, band elimination. We know that unlike high pass and low pass filter, band pass and band stop filters have 2 cutoff frequencies, right. See here 1 and here 2. Same way in band pass filter we had 1 and we had 2, and this was a stop band, this was stop band, this was pass band, right. You don't have to write PB, SP, SP, okay. You have to write stop band, you have to write pass band, you have to write gain. It is very important what you write on the axis. Even you know it is obvious there is a frequency, still you have to mention when you are plotting a graph what is your y axis, what is your x axis. You have to write full form pass band, pass band. You have to write full form stop band, okay. So, whenever you show in exam or in your class or in your interview, if you are asked, please plot everything correctly, please plot everything correctly. Now, it has 2 cutoff frequency when we have band pass and band reject filter. It will pass above and below a particular range of frequency whose cutoff frequency is predetermined depending on the value of components in the circuit design. So, what does that mean? That here in this particular case it will pass all the frequencies below FL and all the frequencies above FH. It will only stop the frequencies between FL and FH. That means this band of frequencies it will not allow to pass, right. Now, any frequencies in between these 2 cutoff frequencies, any frequency between these 2 cutoff frequencies are attenuated, that means they are stopped. It has 2 pass bands and 1 stop band. The added characteristics of band pass filter are shown below. So, it is actually not band pass, but band reject filter are shown in this particular figure. Okay. So, band reject filter. In band reject filter, in band pass filter, what we have seen? We have seen the basic RC low pass filter combined with a RC high pass filter to form a simple filter that will pass the band of frequencies either side of 2 cutoff frequencies. This we have seen in the case of band pass filter, right. But we can also combine this RC filter to form another type of filter that can block or severely attenuate a given band of frequencies between 2 cutoff frequencies, and this is called your band reject or band stop. Now, you see here, you see pass band, stop band. Gain is given by V out in V in. We have in decibels, we have frequency. If it is in logarithmic scale, then we have to write down it is in log, right. If it is not, we have to write down it is in hertz, right, frequency. Now, bandwidth is FH minus FL. This is your central frequency, okay. So, if this stop band is very narrow or highly attenuated over very small range of frequency while passing all the other bands, it is more referred to as band notch filter. What does that mean? It means that if instead of having this bandwidth, if I have like this very narrow band, you see very narrow band, right, then it is called band notch filter. It is called band notch filter. This is because its frequency response was a deep notch, you see deep notch, right here with high selectivity, only that particular small band of frequencies are stopped, right, and it looks like a deep notch. That is why it is also called band notch filter, same filter, okay. Band reject filter is also called band notch. A typically band reject filter response is shown here, alright, is shown in this figure. Now, let us see further. The transformation of this filter characteristics can be easily implemented, as you can see here, right. So, you see this is the band pass band, band stop response, low pass response, high pass response, and here this is the center frequency, this will be the band which is rejected, this is the band which is rejected. Okay. So, if I want to draw this, I can draw this very easily, right. I have a low pass filter, a low pass active filter, let me just clear this one. I have this low pass active filter, I have a high pass active filter, I have a summing amplifier, correct. I have a summing amplifier, is not it. We have seen summing amplifier, we have seen op amp as a summing amplifier. You see the R output voltage fed here. So, it is like V1, R1, V2, R2, right. This output will be RF into V minus RF into RF is this one, RF into V1 by R1 plus V2 by R2, right. This is what we have seen into V in. So, that will be my V out. So, we have seen summer, we have seen the low pass and high pass active filters. When I connect the low pass and high pass active filters in parallel connection, as you can see here with a summer which you can see here, and you have a input voltage with peak to peak voltage this to this, right, and with a particular frequency, then we can design a notch filter or band reject filter by selecting different values of resistors. So, resistance and capacitors of course. So, transformation of this filter characteristics can be implemented as single using a single low pass and high pass filter circuit by non inverting voltage follower. The output from this two filter circuit is summed using a third operation amplifier called a voltage summer, which you can see here, right. The use of operational amplifier within the band stop filter design also allows us to introduce voltage gain, right. So, because we have used now the amplifier, so we can also amplify the signal, that is we can also improve or gain the voltage, we can also introduce the voltage gain. The two non inverting voltage followers can be easily converted into a basic inverting amplifier with a gain of AF equals to 1 plus. So, you see this is the amplifier, this is amplifier, it is nothing but unity gain amplifier, right, unity gain amplifier. This unity gain amplifier we can convert into a non inverting amplifier, right, and we can introduce a voltage gain, correct. We can introduce a voltage gain. Right now, this both are unity gain amplifier or a voltage follower, right. This is my low pass filter, this is my high pass filter, right, but these are just voltage follower. Instead of voltage follower, if I use a non inverting amplifier or if I use a inverting amplifier, then I can easily tune my gain. Thus, we require a band stop filter to have its minus 3 dB cutoff frequency, say 1 kilohertz and 10 kilohertz, a stop band gain of minus 10 dB in between. We can easily design a low pass filter and high pass filter with this frequency requirements and simply cascade them together to form a wide band pass filter design. Same way, if I cascade them in a parallel form, I can form the band reject filter design. So, let us now design a basic wide band RC band stop filter with a lower cutoff frequency of 400 hertz, right. So, FL equals to 400 hertz, FH 2 kilohertz, gain 2, right. Now, we know this formula. So, FH equals to 1 upon 2 pi R1 C1. So, we will get 400 hertz, we have 400 hertz already, right, we have 400 hertz already. So, R1 will be nothing but 4 kilo ohms, right, very easy. Now, same way FL equals to 1 by 2 pi R2 C2. So, we already know FL is equal to 2 kilohertz or 2000 hertz. So, R2 would be nothing but 800 ohms. So, we have found the value of R1, we have found the value of R2, we already know value of C1, we already know value of C2. Do we know it? Yes, we know it, right? C1, C2. Then you see, if I keep value of C1 and C2, I know now I can find value of R1 and R2, I know FH and FL, then I can design the band stop filter. So, now further what is given? Further is given that gain is 2, right. So, let me design a band reject filter with a non inverting amplifier. So, gain will be 1 plus RF by RI, right, RF by RI equal to 2. So, RF by Ri equal to 1 or Rf equal to Ri, Rf equals to Ri, Ri equals to 10 kilo ohm, right. If Ri equals to 10 kilo ohm, right, then Rf will also be equal to 10 kilo ohm, then my circuit will look like the one I have shown on the screen. The circuit will look like the one shown on the screen, is not it. So, I have Rf, I have Ri, I can put a value of Rs, substitute a value of Ri, I have found C1, I have found C2, I have found R1, I have found Ri, I know Rf, I know Ri2, I know R3, I know Rf. So, I can easily design my band reject filter, alright. So, this is how I can design my band reject filter. So, now what we see is using the operational amplifier we can design a band pass filter, we can design a band reject filter, we can design a high pass filter, we can design a low pass filter. Now, once you know low pass and high pass, your life becomes super easy, because using a low pass and high pass in different combination will give us the band pass filter or will give us the band reject filter, right, will give us the band pass filter or will give us the band reject filter, correct. So, now we have also seen how you can design the circuit for band pass, you have seen the circuit for band reject, you have solved some problems for band pass and solved some problem for band reject. Similarly, in the previous module you have solved some problems for high pass, you have solved some problem for low pass. So, now it will be little bit easier for you to understand how the filters would work, okay. So, just go through all the modules for this particular lecture, and I am hoping that you will understand better about how the filters would work and how you can design a filter using operational amplifier, alright. So, the next class what we will see the design of the oscillators, very important topic, and it will have several modules to help you out how we can design oscillators using operational amplifiers. What are oscillators, what are kind of oscillators, what are the problem arises with oscillators, and how we can design oscillators, alright. So, till then what you do is you just look at this lecture, understand how these filters are designed, and if you have any kind of problem in understanding, you can definitely ask me through the forum, and I will try to get back to you at my earliest, okay. So, you take care, read this and have fun, bye.